technology. Mark is one of the known figures in our area, to say the least, but let me just go through his bio briefly to give you a sort of a perspective about his background. Mark received his BA in chemistry, BSc degree in chemical engineering, and BSc in electrical engineering from University of Pennsylvania, and then a SAM and PhD degrees from MIT in 1989. He joined the faculty at Georgia Tech shortly after that, and he now holds the rank of Regents Professor and J.M. Petit Professorships in microelectronics. His current research interests are in the field of microfabrication and nanofabrication technology, with emphasis on new approaches to fabricate devices with characteristic lengths in micro to nanoscale, both silicon and non-silicon materials. Mark is the chief editor of the Journal of Micromechanics and Microengineering. He is also the co-chair of the upcoming Power MEMS conference that's going to be held in US in 2012. But also his other activities, he held the position of the Senior Vice Provost for Research and Innovation at Georgia Tech from 2007 to 2010. So he has a broad perspective about all the key technical areas, particularly what's happening at Georgia Tech. He asked me today, because of his vast variety of activities, what he needs to talk about. And I encourage him to emphasize the system perspective part of his work, because he is the co-founder of this very exciting company called CardioMEMS, which in fact is a success story in our field. I asked him today how many people are working in the company, and he said over 80 people. So he's going to tell us about this CardioMEMS and how they approached it from a system perspective and where it is today, and I'm sure we're all going to be inspired. So with no further ado, Mark.
Thank you very much. And I'm very happy to be here today, and I'm also very happy to be following in a couple of years in the footsteps of my good colleague, Dr. Lossy, being co-chair of Power MEMS, which, as we all know, he was co-chair of Power MEMS 08, is that right?
2009.
09. Yeah. That was right here in Silver Spring. It was a very enjoyable meeting. Well, thank you for the opportunity to speak to you today. And as Reza said, I'm going to talk about some of the work that we've done in implantable medical microsystems. And I've learned a lot about ISR today, and I do think that this could be a good example of how many areas need to come together to form a functional system. The MEMS area, the microfabrication, the clean room activities that we do, the electronic systems that are necessary in order to make a device like this possible, and be able to understand and read out and get telemetric data from deep inside the lossy medium of the human body, the biomedical engineering innovations that are required to be able to deliver these devices using catheters, leave them behind, and in some cases have them exist within the body for decades. I'll talk about this a little bit later, but the very first devices that were implanted back in 2004. So in March of 2004, so now we're getting up to 7 years of implants in people. And so bringing together all of these disparate disciplines to form a functional system, I think, is a very exciting piece of what I've lived through over the past few years. So with that sort of as a little introduction, here's what I'd like to talk to you about. I can't let you get away without telling you a little bit about some of the MEMS activities that we're doing in other areas at Georgia Tech. And then once I've finished that, I'll talk about some of the things that we've done in this system. I don't intend to delve very deeply into the technical details. Instead, I want to just give you an overview of all the pieces that were accomplished. But of course, if there are technical details that you're interested in, everything has been either published or patented. I'm happy to share with you technical details about the system or the device. I'll motivate this. Also, there's a very interesting history associated with this that I'd like to go through with you, which gives us some lessons about what people have done in the past can teach us about the future. Then I'll go through the device itself, the application area of interest, the design and outcome of the clinical trial that was necessary to prove the safety and efficacy of this device, and then briefly talk about what's next. So, starting with my own research group, as was said earlier in the introduction, the overarching theme of our group is the development and utilization of new micro and nanofabrication technologies for the realization of structures and systems. Everybody in my group puts on a bunny suit, goes in the clean room, and builds something. And hopefully, not only is the something that they build interesting and useful, but it's also the fact that they need to invent some new micro or nanofabrication technology, add somehow to the art or science or engineering of micro and nanostructures, and can make contributions in both areas. There are really four major thrusts or theme areas of our group. Microfabricated electromagnetics. I was mentioning to someone earlier that my first graduate student worked on magnetic structures in Madison, probably my last one will, whenever that occurs. That's been a constant in our group for decades. The biological microinterfaces, microfluidics, sensors, actuators, and structures, some of which I'll talk about today. Combustion, power, and flow, and then what I call micro tools for the creation of nanostructures. This somewhat blurry picture was taken, I'm very proud of this picture, at our 20-year group reunion, which was held in Transducers 2009. So I guess both of us have been at this for quite some time. And I was also very honored that buried somewhere in there, you can't quite see, is my PhD advisor, Professor Steve Centurion from MIT. So he has been a supporter of our group and our work since the beginning. Now, that's just some of the things that I do, but I'm not the only MEMS faculty member at Georgia Tech, so I encourage you to take a look at this website. CMMT talks a little bit about our center at Georgia Tech, and if you're interested in more detail and information about what our group does, you can take a look at mems.gatech.edu. Let me introduce just a couple of projects and areas before I get to the implantable microsensor. As I said, we've had a thrust in microfabricated magnetics for quite some time. Some of the work that we're currently doing is focused upon this idea of microfabricated laminations in magnetic materials. And it turns out that these sorts of devices have application in energy conversion. I'm going to show you some examples in a moment. But here are some of the structures that we fabricated. These are some early structures from 5 or 6 years ago where we built up laminations or sheets using electroplating of nickel-iron permalloy core. These are a few microns in thickness. These are hundreds of nanometers or so in thickness. Now, why would you ever care or want to do this? Well, one reason, and this is something that we've been playing with more recently, is forgetting about the magnetics, you have the possibility of building very high surface area materials. At the last Power MEMS, we talked about zinc air batteries that are based on this sort of technology. But in the magnetics arena, we are working on a project that's sponsored by ARPA-E. This is the new agency of the Department of Energy that is associated with electrical energy. Or excuse me, not electrical energy, but energy in general. And can we come up with innovative solutions to solve some of the energy problems that are facing the country? The particular application area that we are interested in is looking at reducing the size and increasing the efficiency of power converters. We're working on this project together with National Semiconductor, and this is this green thing here is a little evaluation board for a switching converter that they have. And there's an integrated circuit chip right there. There's some small passive elements, and there's this huge inductor. And if you rip apart a power supply that's associated with, say, your laptop or your iPhone charger, usually the inductor is one of the largest, if not the largest, components there. And the reason why this inductor needs to be so big is that it's made out of ferrite. It's made out of ferrite because at high frequency, eddy current losses in metals would be too high. And so we need to use a non-conducting material like ferrite, which has a relatively low saturation flux density, so you need a lot of volume to carry the same flux. If you could build this out of metal and suppress those eddy current losses, you should be able to make this an order of magnitude smaller. So that's the focus of our work. If you go out to the back of this building and you take a look at the building transformer, you'll see that the transformer is built up of sheets of iron. And those sheets are bonded together, and the reason why that's done to provide an electrical insulation between each sheet is to suppress losses. So it turns out that the thickness of that sheet depends on the frequency at which the current or the voltage is being converted. So at 60 hertz, like what's powering this room, the thickness of that sheet is a couple of millimeters. But at a megahertz, which is the switching frequency associated with these power converters, those sheet thicknesses would need to be 500 nanometers or so. So we've developed a technology based on sequential robotic electroplating, where we have copper and nickel iron electroplating that's built up layer by layer. So we build up this sandwich of copper, nickel iron, copper, nickel iron, copper, nickel iron, and then we etch away the copper. And when we're done, we have these laminations where we can get hundreds of laminations, and only the people in the very front might be able to see this, but hundreds of laminations that are in the hundreds of nanometer scale. And this allows us to operate these devices at high frequency and take advantage of all the other advantages of metals and suppress the eddy current losses. So that's sort of the focus of our structure. And there's lots of different structures you can make out of this. This is one that we poked with a probe tip so that you can sort of see what keeps these layers together. And one of the nice things about this is, even though the structure is very, very fine on the hundreds of nanometer scale, you can build macro scale thicknesses, 50, 100, 500 micron overall total thicknesses, so you can handle relatively large fluxes. We're targeting with this 10 to 50 watt converters. And we've already built and demonstrated 2 watt converters with efficiencies that are not quite as high as we'd like them to be yet, about 75% or so. Our goal is to push this into the 90% over the next few years of this project. Let me just skip ahead to some of the other areas. We've been playing with combustion, power, and flow. I saw some really, really cool actuators earlier this morning based on silicon and perchlorates that are used to make robots jump around. We've been playing with some other devices, not so much for robotics, but for control of projectiles. And this is not impulse control, the way that you would normally think if you fire a jet with something else. But instead, we release material into the embedding flow so that as the, in this case, I'll call it rotational body, moves through the air, this ejection of material into the flow alters the pitch of the body, and its own momentum carries it into a new target. So in some way, we're amplifying the effect of our actuator by the embedding flow to be able to get more force or more effect of our actuator than we can store in chemical energy within the actuator itself.
Can I ask a question?
Sure.
In the previous one, you were told at all?
Not yet, but we are anticipating, because the whole point of this is to run these at higher fluxes than the ferrites, that we will have them.
Because you go from ferrous to metals, and that's not great for
No, actually, I think the problem will become easier, because the eddy current losses shouldn't be any higher than what's in ferrite, and metal is much more thermally conductive, so we can heat sink it than the ferrites are. The problem that you run into is not that you have more loss per se, it's that you have the same amount of loss in a smaller volume.
And I'm not so much concerned about the loss, but how you get the heat out if you go fire out.
Right, so you do have the advantage of thermal conduction of the metals, which is much higher than that of the ferrites.
Yeah, extraction property.
Sorry.
You have to make the geometry properly.
You can play with the relative spacing of laminations compared to thermal vias within the device in order to balance a particular amount of heat that is generated. We've done thermal simulations that demonstrate that. I'll be happy to chat with you more about that specific project. We're also playing around with micro tools for nanostructures. Is it possible to use MEMS not as an interesting fabricated device themselves, but as a scale or a tool to allow you to build structures in the nanoscale now that build up multi-layers and so on by using MEMS together with metal deposition? This is an example of a movable shadow mask that we fabricated, where the shadow mask can be moved around during the evaporation or deposition to allow you to create or design multi-layer structures in 3 dimensions in the nanoscale. Just skipping ahead a little bit, this was a project that we did just a year or two ago, where we were looking at using molecular imprinting as a possible way to extract this molecule, iodixinol, which is used as a contrast agent in the body for X-ray contrast, but is toxic to the kidneys. Is there some way, and we'll talk about that in the context of the sensor I'm going to discuss with you in a moment. Is there some way to selectively remove this? We prepared a class of materials based on molecular imprinting that allows us to selectively bind and absorb this molecule and discard it from blood. And that allows, one hopes, the use of this material in people whose kidneys, for example, might be compromised or otherwise not able to handle the removal of this material from blood. The last area that we're working on in our lab is this so-called biological microinterfaces. So can we use MEMS technology, which can create structures in the size scales associated with microns and so on, and those size scales tend to match very nicely what's going on in the body, to create interfaces to the body. So I'll just show you a couple of examples. Using molding technology, it's possible to build stents or stent-like materials made from bioabsorbable molecules. We utilize a technique called inclined lithography to build 3-dimensional structures. These are some lithographically fabricated 3-dimensional mold structures that we can then use to mold and replicate not only piercing structures, but by being very careful about how we do the molding and controlling the 3-dimensionality of the mold, we can also, in the same single molding step, create all the interconnects on this 3-dimensional substrate necessary to connect up each one of these posts to the outside world. As some of you know, we've been working in the microneedle area for a long time, certainly over 10 years, and we've been looking at microneedles made of bioabsorbable materials where the payload of the materials is in the tip. And most recently, we've been working on a project looking at can we utilize these approaches for self-administered flu vaccine, influenza vaccine, especially in developing countries where medical infrastructure is not available, where these sorts of devices could be distributed and self-administered by people in those countries. We've been developing some of these into neural platforms. This is a company that started out of back in 2008, spun out of my lab, called Axion Biosystems. We combined some of these technologies for interfacing with neuronal cultures together with integrated circuits that allow you to do suppression of artifacts as well as sensing of the firing of those cultures to be able to look at things like toxicity screening and so on. The MEMS piece is down here, the little multi-well electrode array. And this company is doing quite well. It's up to about 15 people or so, and is currently shipping some of its product. And its fabrication is based on sort of standard microelectrode array on glass fabrication. So you can see that MEMS technology has allowed us to sort of access the body. And what I'd like to spend the remainder of my time on is talking about a slightly different biological microinterface, which this company, cardiomems.com, has been working on. And this is a little picture of one of the sensing chips, and I'll show you a little bit later how it's fabricated and what it does. But it is essentially a wireless, batteryless pressure sensor. It's implanted in various parts of the body, either in the pulmonary artery or in an aortic aneurysm, to be able to sense the pressure at that point in the body wirelessly. Doctors can then measure that pressure and utilize it to guide therapy depending on the particular disease state of the patient. So that's sort of conceptually the device. Now, I'd like to go through some discussion about how this device works and how you might fabricate a device like this. This is a somewhat dark picture, and you'll see why that is in a moment, of someone's thumb, finger. That's the finger there. And there's three little devices on the finger. And what these devices are passive inductor, capacitor, resonator, transducers. And I'll show you in the next slide how these work, but basically buried inside here is an inductor and a capacitor. Pressure changes the capacitance of the capacitor. That shifts the resonant frequency of the device. If you can read out that resonant frequency, then you can say something about what the embedding pressure must have been. It's a very simple and straightforward electrical engineering concept. There's no internal electronics or battery. They're small. They're powered by external inductive coupling. And they've been demonstrated to be implantable and functional in animals. And the concept, as I mentioned, is very simple. Imagine that you have a sensor, and there's a vacuum or a cavity here that's encapsulated, encapsulates vacuum. There's a plate on the top and on the bottom. As the embedding pressure in which this sensor is sitting changes, those plates deflect ever so slightly toward each other or away from each other. If I have capacitor plates on this device and an inductor coil on the outside of this device, I've formed an inductor and a capacitor structure. As the pressure changes, the resonant frequency of this changes, and I can read it out with an external loop antenna. And if I know something about the mechanics of the device, then I can trace this frequency that I read out all the way back to what that deflection must have been, and then from that, what the pressure must have been on the device. That's basically the concept. Now, it turns out that, that this device works quite well. So here's that same picture with the finger with the three little devices. The smallest one is 2 millimeters in diameter. The largest is 6 millimeters in diameter. And what I've shown here is a plot of the resonant frequency of this device in megahertz, between 0 and 160 megahertz, as a function of the coil separation, not quite the pressure, but the separation of the top and bottom pieces of this sensor. And you can see that you do trace out a curve, and therefore it can relate the frequency that you measure to the coil separation and therefore the pressure. Now, this is not work that we did in our laboratory. This is some work that was done by Collins, and it was published in the IEEE Transactions on Biomedical Engineering in April of 1967. April of 1967. So it's been 50 years, 45 years that people have been thinking about this. Actually, it's been longer than that, because if you go back in the literature, you can find some even earlier references. Now, I want to just take a minute and go through the way that this thing was fabricated. So those of you who are toiling away in the clean room will appreciate the effort that had to be gone through in order to make a device like this. So in MEMS, we always start with the substrate. So in Collins' case, the substrate was a short, thin-walled glass tube. So the chemists know this tube. They use them for pipetting, right? You then take this glass tube as your substrate, and then on a Teflon sheet, you take a flat Teflon sheet and a little wire, a lot of patience, and you wind a little spiral by hand on this Teflon sheet. So it looks something like this on the top. And then when you're done, you take some shellac or nail polish or something like that. You paint it on the top to hold the coil in place. You then take these two coils. You put one on the top of your little tube, one on the bottom of your little tube. You stretch them around. You take some heat shrink tubing and heat it up, shrink the tubing around the tube, and you wind up with your sensor. Pretty impressive, especially it's pre-MEMS fabrication technology. And it's not even the earliest one, I think. As I said, this happened in 67, but earlier, all the way back to 1957, so now it's over half a century, people have been thinking about this technique as a way to get information out of the body. Now, why didn't these things work and take off, and why haven't people had implants like this for the past 50 years? Well, the major reason is the reason that I showed you. The fabrication technology to create these kind of structures just didn't exist at the time. And as you can imagine, these devices had all sorts of drift issues and stability issues and so on. And in addition to that, the electronics that was necessary in order to read these out would fill up this room with vacuum tubes, literally. If you go back to Collins's paper, you'll see the circuitry. And also could only read out about this far away. But just like we had these enormous progress in MEMS and fabrication technology over the years that have sought to address this, we've also had this enormous revolution in electronics and telecommunications technology, which has improved by many orders of magnitude the sensitivity with which we can collect these signals. So even though the ideas have been around for a while, the means to implement them have only just come into existence. So that's one of the reasons why this is a really exciting time, especially for the students in the room, because all this technology is now at your fingertips and you can do all kinds of interesting things with it. Now, how did we get started with this? Well, this was a project that we did back in the mid-90s, and it had to do with building a passive resonance sensor for turbine engines. And this particular work I'm going to show you was published in the Proceedings of MEMS in 1999. So now it's no longer half a century, but it's only a decade or so old. Actually a decade and a half when we got started. This was a MURI project associated with measuring the pressure inside of turbine engines in order to understand where the onset of surge and stall might be in the turbine engine compressor. Now, it's a pretty rough environment in there, 500, 400, 500 degrees C operation temperature. Batteries, circuits, and so on would have a hard time working in there. So we decided to build one of these passive resonators. We built it not out of silicon, but instead we built it out of ceramic. The particular ceramic that we used was aluminum oxide, either low temperature co-fired with glass or pure aluminum. And we were able to build up, using this green sheet technology, which you may be familiar with, coupled with lamination, multiple sheets consisting of coils on the top and bottom, cavities that allowed us to create the encapsulated cavity for this device to operate. The way this is fabricated is these individual sheets are all brought together, laminated and co-fired, and you wind up with a block of ceramic encapsulating the cavity with all of the coils and so on fabricated inside. So here's an example of some of that work. Here's the cavity here is about 250 microns or so. All of the coils and the capacitor plate to form the sensor are all embedded inside of this device. So this is something that turned out to be key for enabling a MEMS product, which is that the package is co-fabricated as part of the actual sensor itself. You don't need to go and find another package that's biocompatible, or in this case, engine compatible. Instead, the package and the sensor are one and the same. This picture is backlit so that you can see some of the coils sort of through the thickness of the device. Now, when we think about taking these devices and putting them in people, we notice that the engine itself is a pretty harsh environment, and so is the human body. So maybe we can transplant this material into human body application. So if we're going to think about something that has to be stable for decades, right? Somebody might have a sensor implanted when they're 50 or 60, and they might live for several decades afterwards. We have to worry about the things that might cause the sensor to drift. And there are three major things that might cause this device to drift. What if the pressure reference, that cavity inside, changes pressure because of molecular leakage in and out? Obviously, heat shrunk plastic is probably not going to be able to withstand molecular penetration for over a decade time period. So we have to make sure that's hermetically sealed. We have to worry a little bit about overgrowing tissue on the sensor, affecting its calibration. Right? If we have a sensor that's relatively flexible and the body grows tissue on the outside, we have to make sure that that tissue doesn't affect the overall calibration of the sensor. So that sets a maximum limitation on how flexible we can make the device. And then we have to worry about corrosion and fatigue in this harsh, chemically harsh and moisture-filled environment. I had the experience, I guess you'd call it, of seeing an exhibition of material from the Titanic, the boat that sunk a century ago, when it came and toured and visited Atlanta. One of the things that struck me was that the ceramic materials, the plates, the cups, all of that were dredged out of the ocean, were quite brand new. It was like they had never, obviously they cleaned them a little bit, I'm sure, but it was like they had never been submerged for a century. The ceramic materials really are tremendous materials in terms of corrosion and ultimate fatigue.
A question about the sensor that has the overgrowth of the tissue. It's clear that the body's going to lay this stuff on top of it. So how do you calibrate, not knowing how much you're going to get on top of it and still be able to measure what's happening inside?
Yeah, that's a great question, and the answer is I don't know. But the only thing that I can do then, since I don't know whether the body is going to grow, not only whether the body is going to grow, a millimeter or half a millimeter or 2 millimeters, your body and my body will do it differently. So the only thing that I can do is design my sensors so that the stiffness of the sensor is much, much larger, the flexural rigidity is much, much larger than the flexural rigidity of anything that the body will put on top. So as a result, I have to make my, and I'll show you a little bit later when I show you how it's fabricated, I have to make sure that that sensor is so stiff and moves so little that the perturbation associated with tissue growing on the outside is negligible.
Does this restrict your lifetime?
No. In fact, it does the opposite, because now the amount of excursion or amount of strain with each, in this case, pulsation of the heart is small. Absolutely. And as you'll see, the materials we've chosen are resistant to that as well.
Are there any cycles for money? When I put things in the body?
I'm going to tell you. So the short answer is yes, but there are ways to solve that problem. I guess that's actually the second bullet here. The biocompatibility really restricts your material set. If the perfect material is plutonium arsenide, then that's not very useful. Right? So you have to think about that a little bit. And then the third piece is the readout distance. There are some applications that require sensors to operate deep within the body. And by deep, I mean tens of centimeters, 30 centimeters. In one of the applications that I'm not going to talk about today, the device goes in an aortic aneurysm, which is right about here. And some people, their belly is out here, and often it's people that are obese that wind up needing some of these devices and implants. So you have to be able to design your electronics in such a way that you can really focus in on this very, very tiny signal that's deep within the lossy medium of the body. But luckily, as I said before, we have all this progress in MEMS fabrication technology we can exploit, all this progress in electronics that we can exploit, and so as a result, we think that now, finally, after all this time, we can do it. So let me move on and talk about the particular disease state that we hope to treat with this device, and how it's done and what some of the results are, and I'll speed up a little bit here. In the case of heart failure, it turns out that heart failure has changed from an acute disease to a chronic. If I look at the coronary death rate as a function of time from about 1980 to 2000 to 2003 or so, coronary deaths are down by half. So if you have a heart attack, it used to be in the old days that you didn't survive. Triumph of medical technology has allowed people to survive. But the problem, if you want to call this a problem, and it's good problem to have, because the alternative was death, is that people have to live now with damaged hearts. So a damaged heart that before would have killed you, you can now live with, but now you have a chronic condition, your heart is weakened, you have to take medication, you have certain regimens that you have to adhere to. The doctors need data to treat this condition. Now it turns out that not only does this affect quality of life, but it's also a tremendous expense on the public and private treasury. So this is back from 2003 now. The estimated total direct cost of this chronic heart failure condition on the order of $20 billion per year. Of that, $15 billion is this chronic maintenance condition where someone with a weakened heart has to go to the hospital, has to be given medication, quieted down, put back under control, compensated, so to speak, and then can go home. So if you could give the doctor better data so that you cut down on the frequency of these events, then you would be able to save an awful lot of money. And it turns out that in the same way that blood glucose can be used as a marker to allow appropriate dosing of insulin for people with diabetes, physicians know that intracardiac pressure, the pressure inside the heart, can be used to treat heart failure. So if I know what the intracardiac pressure is in the heart, then I can adjust medication, beta blockers, diuretics, and so on, that would then allow that pressure to come down to an appropriate physiological range and allow people to have a healthier, yet still a healthier experience, yet still live with this chronic
Well,
heart
you
failure.
get the fat person, we can do the ratings and we know about it.
Well, I think we have many medical approaches to solving this problem. So let me tell you a little bit about the device that we fabricated. It is a very MEMS-oriented fabrication process, but instead of using silicon, we use silica, fused silica. You can buy these wafers, they're available, just like silicon wafers. They are very, very flat, optically flat, in fact. We take one of these wafers, it's typically about between 100 and 300 microns or so in thickness, and we etch using wet etching, HF, a recess in this. We then use photoresist and electroplating to deposit electroplated windings within this recess. So if you squint at this device, it looks like a little racetrack is running around here. That's the L part of the coil. We then take a second one of these devices, flip it over, align it with the first one, and then fusion bond these silica pieces together and dice them up. And we're left with this sensor device. Very straightforward fabrication sequence. The package is fabricated at the same time as the sensor itself, as I mentioned before. We can then do things like coat the outside. You'd asked about previously the issue of interaction with the body. We coat these with a silicone material. So it's silicon dioxide, which is already inert. We coat it with silicone material, and it turns out that when it's inserted into the body for a few weeks, the body grows a layer of epithelial cells around it inside of a blood vessel. It's inserted inside a blood vessel, and then after that, it seems to be inert. So that's
How much
nice.
data you have actually on this growth tissue or other
A lot.
from the devices you have?
A lot.
How do you get it?
How do we get it? By histology and animal testing.
And so you take, put the device in and follow them over the years.
Yes. Obviously the FDA requires enormous amount of testing along these lines to make sure. I'll tell you a little bit later about where these devices are implanted, but they are implanted in the pulmonary artery. We have not seen any evidence of clot formation or anything like that, but if there were to be a clot, the clot would not travel to the brain or somewhere where it would be on the left side, instead is on the right side of the heart, so it would travel downstream.
What's the size scale of that?
We've built these in all different size scales. The current devices, I believe, fit inside of an 11 French catheter. So they're about, trying to remember, these are large, these are actually the aneurysm devices. The heart failure device is currently centimeter length, something like that.
The whole thing.
You don't have the basket on the ones that you put in the catheter.
So these baskets are used to secure the device within the vessel so that it remains sort of in the center. They're made of nickel titanium wire. They're nitinol, so they can be squeezed to move down. The baskets that we use for the heart failure sensor actually look a little bit differently. I'll show you a picture a little bit later. They're just one loop that juts out here and one loop that juts out here. They have no electrical function. Their only function is mechanical. Now, thinking about this as a system, the sensor is only one part. Here we go. So this is the device that we have been using in our clinical trials, about 1.5 centimeters long, 3.5 millimeters wide. Thickness is about 2 millimeters. And there are 2 loops. As I said, they have no electrical function. They're just used to anchor the device in the artery. But this is only a small portion of the overall system. There's a, yes?
How do you get those things in? Do you have to compress them?
I'll show you that. Those are the other pieces of the system. We use a catheter. The catheter is similar to a Swan-Ganz catheter that's used to sense the pressure inside the heart currently. The device itself, this is the catheter kind of folded up. Here's the end, and this little tiny blob right here is the sensor itself. So the doctors thread the catheter in, pull the equivalent of a ripcord. This thing comes off, and then they pull the catheter back on.
What do you have to replace them?
I'll show you that as well. There's a third part of the system is the readout electronics necessary to communicate with the device. And then the last part of the system is, and some might argue the most important part, is the measurement database. So the measurement database, which is a plot of, in this case, systolic, mean, and diastolic pressure as measured by the sensor as a function of time, allows the doctor to guide medical therapy. And it's very interesting. You can get lots of information out of this, not only how best to guide medical therapy, but also whether patients are being compliant. So for example, here you can see the systolic pressure of a particular patient falling with time. The doctors have things under control. Looks pretty good. And then there's this little spike here. That little spike happened on the 4th of July when this patient went out and had a barbecue. And then came back into work. So there's lots of interesting things that you can find out. The doctors can not only get information like that, but they can also get, should they like, a full tracing of the waveform as a function of time. We interrogate the device at approximately 120 times a second, which allows us to resolve up to 60 hertz, which is enough to get all the fine features within the waveform. And the fundamental here is on the order of 1 to 2 hertz, as you can imagine. We can get systolic pressure, diastolic pressure. These look low, but remember this is on the right-hand side of the heart. This is not the high pressure left side where you get the 120 over 80 kind of reading. You can get the heart rate, and you can also, by integration, get the cardiac output, the total volume of blood that the heart is pumping. So there's a lot of information buried in here, should you care to look even further.
So there still is the question of what do you do as the tissue is building? It's going to be changing the measurement, right?
No, that's the key. It's not changing the measurement because you built the sensor so stiff that whether you have a small amount of material or a large amount of material on the sensor, it doesn't matter. It's still controlled by the stiffness of the sensor.
Yeah, I think it would be more.
Relative, because it's the relative change.
Right. So what do the doctors typically do with these patients? Well, here's a typical case history that came through from our from our clinical trial. This is a plot of pressure in the pulmonary artery as a function of time. And this sort of gray zone here is what the pressure should be physiologically for a healthy person, quote unquote. Now this is a person who is 52 years old, so this is somebody who is not that old, right? 52, at least from my point of view, not that old. But maybe to some of you it's old. And this is somebody who's pretty sick.
It's a youngster.
This is somebody who has cardiomyopathy, already has a pacemaker, has hypertension, atrial fibrillation, gout, sleep apnea, and so on. And this is not somebody who is vastly overweight or anything like that. The BMI is 26, weighs 176 pounds. So this is a normal person who unfortunately is not blessed with good genes. And these are somebody that could potentially be alive for many decades. And this is sort of the design lifetime that we have to think about for this device. So what do the doctors do? Well, they take this patient, they treat him the best that you can. I know it's a him, it says male here. And what they found was when they were treated according to the gold standard, when they were checked out of the hospital and went home, their pressure was still too high. So the doctors started to fool around with, I shouldn't say it that way, to intelligently change the medications that the patient had. And so each one of these green boxes at the top here is something that they did. They gave a little of this, they changed the dosage of that, they pulled this one away, and so on. And you can see that the concentration of green boxes is very high in the beginning until they figured out what worked well for this patient. Or, alternatively, and I'm not sure which one of these is true, the body takes a certain amount of time to respond to those medications. Whichever it is, likely a combination of the two, at some point the pressure falls and it can be guided into this physiologic range. Interestingly, there are occasionally opportunities to go back and measure the pressure using the Swan-Ganz catheter. So here's an example where almost a year later, it was necessary to go back and with this patient measure the pressure using the Swan-Ganz catheter, and allowed us to compare that to our sensor, and we found that they agreed within 2 millimeters of mercury even after a year in the body. So we were quite pleased about that. So now let me tell you briefly about the clinical trial that we just completed. It is was just published in The Lancet about a month ago or so. And the objective was to evaluate the safety and efficacy of this system in reducing heart failure-related hospitalization. So the endpoint was, are people whose medical therapy is guided by the system less frequently in the hospital than people who are guided by the current gold standard of heart failure chronic care? So that was the question. This was done, originally presented at the 2010 European Heart Failure Conference. Again, as I mentioned, it was just published in The Lancet. The PIs are from Ohio State University, Dr. Abraham and Adamson. I'll skip through some of the details here, but there were 550 people who in this clinical trial received an implant, 63 sites across the United States over a 2-year time period. And as I mentioned before, the group was divided into 2 pieces, blinded. One group received traditional heart failure management guided by, one group received management guided by hemodynamic information from the sensor. The other received just traditional heart failure disease management, what you or I would get if we were in this position without a sensor. And then they were compared. The hospitalization rates were compared. Now, there were a couple of questions about where this device is implanted. If you look at the pulmonary artery is the one that comes out of the heart and carries oxygen-depleted blood to the lungs, where it then gets reoxygenated and pumped back into the body. And the pulmonary artery starts out as a very, very large artery, and then it breaks up into individual branches, which then break up into finer and finer branches, and ultimately into into arterioles and capillaries where the actual gas exchange occurs. And deep within this network is where we place the sensor. So we don't place it right here at the output of the heart, because if something bad happened, then that would block the entire output of the heart, and that's not good. But if something bad happens down here, and I'll show you how many bad things happened, none, thank goodness, then it is not life-threatening for the patient. So the device is threaded through the heart using this Swan-Ganz catheter. So it's through the heart, out through here, into the target implant site. The ripcord, so to speak, is pulled. The device separates from the catheter is pulled out, and the device is left behind.
How is that guided?
It's guided through the,
But I mean, is there an imaging? Yeah, at the time? Or how does the surgeon know?
yes, so it's done with contrast. Remember that idixonol I showed you before is injected into the body, and it's followed angiographically. So it's just like getting an angiogram. So the demographics of the patients, as I said, these are young people, right? 61 plus or minus 13. That's 60, 59, 58, minus 10, 48. It's 48 is the youngest patient. That's a little scary. To give you other ideas, 2/3 of these people had ICDs, cardiac defibrillators. 1/3 had pacemakers, and all of them were already on medications because they had heart failure. Now, some of the things that we saw as a result of the clinical trial, we had things like looking at failures of the sensor. And after we saw this, we went out and bought our engineering team a glass of beer. No failures of the sensor were observed during the trial. We were very pleased to see that. And what we saw, maybe most importantly out of all of this, is this primary efficacy endpoint. So this is the reduction in hospitalization for those patients who are treated by the sensor versus those patients who aren't. So what we saw was that there was a reduction of 30% in hospitalizations for people who were treated, whose therapy was guided by the sensor data, compared to those who were guided by a standard, current gold standard of HF treatment. And the p-value, which is 1 minus the probability that this was occurring by chance, or maybe I should say it this way, the probability that it was not chance was 99.95%. And so the probability that this could have occurred by chance was only 0.005%. So clearly, to my mind, clearly the sensor is statistically significant. Now, if you look at it on an annualized basis as opposed to the 6-month basis, the effect continues to increase, and now 38% of people have reduction in hospitalizations. Excuse me, there's a reduction of 38% in the number of hospitalizations. Now, there's this is the same data but presented graphically. If you look at the cumulative number of hospitalizations of these people with heart failure as a function of time, you can see the blue curve is the control curve, those who were treated by the current gold standard. And as you would expect, the hospitalization rate goes up over time. And the red curve are those who were treated according to data from the sensor. And so the gap between the red and blue curves are the hospitalizations that are saved. And you can see a very significant and growing gap as time goes on between the sensor-treated patients and those that weren't. The other interesting thing, at least to me, is what happens at the very beginning. So this, at the very beginning, maybe for the first 70 or 80 days, it doesn't look like there's any difference between the two. And then you start to see this divergence. Well, if you remember back to that data I showed you on that poor 52-year-old patient, it took about 70 or 80 days for the doctors to get the medication right, quote unquote, to push that patient's pressure down into the physiologic range. And it's interesting and suggestive that it also takes about that same length of time for you to start to see a difference between these two. So that's sort of an interesting.
So did you say you have over 600 subjects? 600
550 in this clinical trial.
It's about half of them, they got treatment?
Half got treatment, half got,
No,
all had sensors implanted.
So if
Half-
you go back to the figure, it seems half of them, they went to the hospital. If you see the blue curve,
Uh-huh.
after 900 days, this curve goes all the way over.
This is the cumulative number of hospitalizations.
Oh, I see, so maybe one person was the
Went multiple times, right?
So the people with, that were monitoring the sensor were in the hospital because of non-pressure related issues, or they never got the medication right, or why did they go?
So it's normal, quote unquote, for people with heart failure to wind up in a state called decompensation. And I don't know if you've ever heard of the term congestive heart failure, but congestive heart failure is when the body or the heart cannot pool, I guess you would think of it this way, enough blood from the lungs in order to circulate throughout the body. And so as a result, it's not really blood, but it's liquid, backs up into the lungs, and you wind up with a condition that seems like you have congestion or cold, you're coughing a lot and so forth. That's why it's known as congestive heart failure. It's quite common during the progression of this people with heart failure and congestive heart failure that they will wind up in this condition. And when that happens, they have to go to the hospital, and then the doctors put a pressure catheter, currently, they put a pressure catheter in the pulmonary artery or the heart, and they start adjusting the medications. They start doing all these things that I talked about with the catheter kind of hanging in there until they get the patient better, until the heart is able, through medication, to be able to get back into a compensated state. Then they go home. Each time that they do that, the patient gets a little bit weaker, and ultimately they don't survive. So if you can keep them out of the hospital, then you not only improve their quality of life, but maybe, I don't know, this hasn't been statistically demonstrated, but maybe you can extend this.
What is the medical treatment?
The medical treatment,
Without the sensor, how do I actually follow the doctor? And the more important question is, do I actually need a doctor?
you actually
Do I actually need a doctor?
need a doctor? Well, the way that it's currently managed is through these medications. And so maybe one way to think about it from an engineering point of view is
I follow telemedicine and medicine for many years, so let me give a better answer to you.
okay,
As
well,
far as in particular the last question, whether we need a doctor.
okay. So the short answer is yes, unless you can prescribe your own medications, you need a doctor.
But there are a lot of things that you can be followed without a doctor. It can be followed by lower level medical personnel and technicians and others to identify the condition without and actually this is a very big reason why medical expenses in the country is so high. Because you are this is a long discussion, but a lot of evidence that many of these very well understood problems can take care of them without the expensive part of the medical system in the hospital.
Yes, but I would argue that this is not a particularly well understood problem yet. But
That's why I asked you, what actually happens if I have
So-
a condition, then what do they do to me, or how do they follow me if I don't have a sensor?
So the way that this is typically done now is you go to the hospital, you have this congestive heart failure condition. You need a cocktail of medications to allow your body to operate normally, quote unquote. You still have heart failure, still weakened ejection fraction, your heart is not pumping well, but you need some combination of medications. What are those medications and what are the relative concentrations of them? The doctors will put a catheter in your heart, will adjust the medications until they get the pressure into the range that they like, then they take the catheter out and send you home with those medications, and the whole thing operates over loop until the next decompensation event.
Now, if I have a sensor, I can take medications.
I'm sorry?
If I have a sensor, again, I can take.
You have to take the medications, but now you have the possibility of adjusting the medication prior to the decompensation event, which then allows you to stay out of the hospital longer, and that's what our clinical trial showed. There are other things you can do as well. You can monitor weight, as you pointed out before. There's stress testing that you can do, and so on, but really the medications are the...
If you cannot test the condition that you try doing 5%
You can look at physical blockages by angiography, but it's hard, it's not impossible, because you can do things like Doppler velocimetry, things like that, but it's hard to measure pressure.
Sure.
And in addition to that, angiography requires dye is toxic, and things like that. What you really want is something where you can get that information easily.
Does the symptomology of congestion interfere with the measurement since you're down in the lung speed with the sensor?
No, because we are not so deep in the lung that we're near the alveoli. We're still far up from that.
So obvious, there are some malfunctions of the alveoli that
So where to put the sensor is actually an interesting balance between being close to the heart, which is what you're actually trying to measure, and being far enough away from the heart that if something bad were to happen, you don't affect the body system. And so that's how the doctors decided to.
You also know what a blocker is.
Exactly.
How do
That's
you
it.
get the damn thing out if something goes wrong? Sorry for the language. Sorry, but remember, you're not reverse the part.
You're being recorded, so be careful. But maybe they can't.
I
Maybe they
think we're saying a
can't.
lot worse things than that, but that's okay.
Yeah, really.
So the short answer actually is that we don't take it. It stays in forever. However, we can take it out. We demonstrated that in animal tests. You can. There's a catheter device that doctors call a snare, and you can thread this catheter in and grab hold of either the sensor or one of the loops of the sensor, and then pull it back out
From the artery.
from the artery. That was demonstrated in
Definitely
animals.
don't want to go cut arteries or things like that.
Right, exactly.
It's a lot more expensive than when you're trying
But
to avoid.
you're going into a greater diameter than you started at.
It's angled.
No, I know, but then when you're pulling it back.
Tissue around.
That's exactly right, and that's why we don't recommend, and we don't pull it out. But the question was asked, could you, if some terrible thing happened? And the answer is yes, you could. And just like, could you remove a malfunctioning pacemaker? Sure, you can, but it's tough, and it's not good.
Have you ever had to put in more than one?
And we've never, that's a good question, and we've never had to take one out. I just want to make sure that that gets on the record. In our clinical
Because I have a whole
trial,
series of questions that come from the engineering side, which go like the line, do you have any estimate of the life cycle, fatigue, and things like that, as you will ask?
Oh, right.
absolutely, absolutely. The FDA requires all of those.
We're now with the version 2014, now about 80 years.
Yes, but of course, there's accelerated testing, which
So what is this net life?
our
Design
design,
lasts forever, right?
right, our design specification was a decade, but we've done accelerated testing out to 2 decades and really found no or little effect.
No loss of performance.
Correct. But still, 2 decades in the body might be different than 2 decades worth of accelerated testing.
60 and 2 days, and hopefully you hope to use more than that.
Exactly right.
At least I think.
So that goes to your question, can you put in more than one? And in fact, the answer is yes, we've demonstrated that as well in animals. You can put in more than one device, and if each one has its own resonant frequency, you can read them out independently. And we demonstrate that you can also do flow sensing that way. If you know 2 pressures along a tube, then of course you can calculate the flow. Well, let me end by showing you a little video. And it might take me a moment to figure this out because of the various complications here. So bear with me a moment. Because unfortunately I can't play this from the stick because I can't plug in the sound
You can.
and have my USB stick in the same time. So Steve Jobs, who normally does everything perfectly, made this one little error.
This is a medical first. A heart failure patient at St. Joseph's Hospital is the first person in the Southeast to get a new implanted device. The device is based on technology developed at Georgia Tech, and it monitors a patient's health from home, saving time and money. Channel 2's Dr. Randy Martin was in the operating room for this procedure.
I got real sick. I was out in Wyoming, and it took me about 3 days to get home. And I didn't realize that I just thought I had food poisoning.
But Dan Miller had actually had a heart attack, one so severe that despite having a bypass operation, he ended up with heart failure, a condition that affects nearly 5 million people in the U.S. And one of the keys to managing heart failure and keeping patients from being readmitted to the hospital is to be able to closely monitor the pressure within the heart and the blood vessels. And now Dan is becoming a pioneer, having this tiny device implanted.
This is a CardioMEMS pressure monitor and a pressure sensor.
This device, which will function as an early warning system, is wireless with no batteries. It's technology developed in part at Georgia Tech, and here's how it works. The device is implanted in the artery going to the lungs, the pulmonary artery, and once in place, it can measure the pressure in that artery and the heart, as well as the amount of blood the heart is pumping each minute.
No, I'm fine.
You did fine, okay. Dan is awake during the procedure as Dr. Ravel and his team deploys the device. And within a matter of hours, Dan will go home, where he will simply lean against a pad the size of a small pillow, which will record the pressure readings from his heart and send that information wirelessly to his doctor. Information which may allow doctors to tell when patients like Dan are beginning to develop worsening heart failure, so they can be treated early, often at home.
I feel quite honored to get this done because a lot of people won't maybe get this chance.
For Channel 2 Action News, I'm Dr. Randy Martin.
The device can also tell the doctor when a patient should come in for a visit, and those visits are far less expensive than trips to the emergency room. We have more.
Great, thank you.
Well, let's type our Excellent. Okay, now we're ready for questions.
I'll let somebody else.
Yeah, let's give some time to students at the back so now they can ask us maybe questions.
My question was sort of answered in that video, but so you read it out with that paddle or a coil. Do you guys have some kind of system then that just so that person is given instructions where they have to, for 1 hour a day, they have to sit, or for however long, they have to sit with this? Does it get recorded to like a smart card that then gets mailed? Well, my wife has a CPAP machine, and that's how that works. Usually they record on this card, but she still has to send it in. Do you guys have it set up so that it's direct, like it automatically sends it, or does the patient still have to send like a device?
No, it automatically sends either over the internet, over plain old telephone system, or using a cellular modem. And it's quite interesting. The way the doctors have chosen to use the device is management by exception. So there's an enormous amount of data that comes out for each individual patient. And now imagine you multiply that times the number of patients you might have in your practice. How do you keep track of all of that? Well, what the doctors have done is they've set certain limits for individual patients. And then when the pressures exceed those limits, they get an alert. And sometimes, to the question about healthcare costs, sometimes those alerts go to a nurse. Sometimes the doctors elect to have the alert show up on their own Blackberries. I've seen everything from that one end of that spectrum to another. But no, it is trying to use the internet and cellular or telephone communication to relieve that patient of that burden.
I guess trying to also remove any kind of patient error or anything. Because that's a big problem, I think, is that a lot of these or these monitoring devices, there's still that one part where the patient has to send it to the doctor or has to get that information to the doctor. And if they forget, so that's really cool.
Right.
So it's all integrated, built in.
It's all integrated, and the thing you have to remember is that not every patient is as alert as this patient was that's here. Some of the people are quite elderly. And being able to design a system that does require patient use. The patient's got to lay down and press a button. That's the extent of what the patient needs to do. It doesn't require any other patient intervention is important, I think, in that case.
You don't want to put in something like air sports or something, so that, because one of the things that we people considering these automatic or something local that put the test with local.
One of the things that's has been speculated to be important, and I don't know if it's important or not, but I suspect it is routine. So you're doing relative comparisons day to day, looking for changes. And so if one day you, so let's imagine that you hang an antenna on the ceiling, or just making it up, right? And one day you get a reading, or 1 hour you get a reading when the patient just stepped off the treadmill, and another hour you get a reading when the patient's in bed. This actually allows you to the patient have a routine. They're lying down, they typically do it at the same time every night, and so on. They're quite motivated to do it. And with some of them, it's quite interesting. In some of the very early, especially with our aneurysm sensor, we had a lot more interaction. The patient had a lot more interaction with the device. Here we've tried to keep the interaction to a minimum for the reasons we just discussed. And the patients would take in the antenna and they move it around on their belly and they try to make the signal strength go up. And all of this is almost like a video game or something like that. But this routine, I think, helps and allows us then to pick out things like that 4th of July incident that I mentioned. Warning.
Yeah, I just want to ask, is the device cost-friendly, and I guess insurance is interested in covering it because it reduces hospital? So.
Yes, that's exactly right. Now, since this device has not been FDA approved yet, we just finished the clinical trial, there is no price that's been set for it yet. But the other device, the aneurysm sensor, has been FDA approved. And I believe its price is something like $3,500, I believe. When you compare that to the cost of, in the aneurysm sensor case, the burst aortic aneurysm, or in this case, hospitalization, which may cost tens of thousands of dollars, it doesn't take very much cost savings to justify the price of the device.
Sergio.
In your final device, you clinically tested, what's the distance of operation of the inductive channel? And a second question related to that, what's the frequency?
So, good questions. The distance that we typically use is about 30 centimeters or so, this sort of distance. The frequency that we use is between 30 and 37 megahertz. Relatively low frequency, and you might then ask why choose that frequency. If you think about this from a resonant sensor point of view, the higher the frequency, the smaller the sensor. The lower the frequency, the less attenuation you have in the body. So those are kind of the two pieces that define your design point. And we found that this so-called HF high frequency band, these bands were named 30 to 37 megahertz was high frequency. That HF band was a very good compromise between those. So that's why we chose it.
Actually, a related question, is that what led to the size choice of the 1.5 millimeters? I mean, it's bigger than you could presumably make, right? So the size of the sensor, what led to that choice of how big you made the sensor?
So there are two things that go into the sensor size. If you're asking me, is that a limitation of the technology? Clearly not.
Yeah. Okay.
Right. So you can make the device much, much smaller than that if you like. And we've made some devices that could be inserted into the radial artery, for example, of the wrist and read out with a wristwatch, as you mentioned. Now, I would say what defines the physical size of the device is two things. One is the medical condition that's being treated. So, for example, in the aneurysm sensor, they don't even start treating abdominal aortic aneurysms until they are 4 or 5 centimeters in diameter. So, that big. You want a sensor that's going to be able to sample a reasonable fraction of the space. And there's a medical device there. In the case of this sensor, the size is also set by the, I'll call it electrical cross-section will, of picking up the interrogator and sending the information back out. So in addition to that, there is a minimum size that we could make this particular sensor as dictated by the signal-to-noise ratio in doing this. But this device, I didn't show you a cross-section of it, but it typically consumes only about 10% of the cross-sectional area of the artery in which it's implanted. So you still have 90% of the flow, and that's confirmed through angiography and so on.
And it doesn't do anything like set up eddy currents, quite a blood flow behind it, or anything like that?
In these locations, no. And remember that this is in the right side of the heart, low pressure sorts of devices. I thought you were going to ask me about the other kind of eddy currents. In other words, how much power do we use to interrogate this device?
Last question.
So let me answer my own question.
Okay.
The reader typically puts out an average power of about 600 milliwatts.
Okay.
So relatively low power.
Kind of along these lines, and in reference to something you mentioned toward the end of your talk about multiple devices with different harmonic frequencies. Now I know that there's some commercial like microelectromechanical devices that they have to characterize each device because there are subtle geometric differences in pattern. Is it directed by you guys that each device have a different frequency, or do you deliberately have like, something at 31 and something at 36?
So our typical application does not require multiple devices. So in our typical manufacturing, we shoot for a particular sensing frequency and sensitivity, and we have a range that is acceptable within that, and we calibrate all of the sensors. And if they fall within that range, we use them. And if they don't fall within that range, we don't use them. If we knew for a fact that we had a patient where, for whatever reason, the doctors wanted to put in multiple sensors, then we might choose from the low end of that range and the high end of that range on purpose. But we don't manufacture them on purpose to have two different frequency ranges.
Okay, so I guess the message is that NEMS even works in the body. Thank you. So Professor Allen is going to stick around for a few minutes if you have any more questions.